The purpose of this video is to do a test hypothesis for a single population proportion. But before I do that, let's go and take a look back at our two different methods of comparing or evaluating test statistics. So the two methods are rejection regions and p-values, and what I want to do to start is to compare the two. And what you see here is a very odd picture. What am I doing? Well, I want to zoom in to just one side of a normal distribution. So let's say we have a large sample, n is equal to 200, so that's a large sample, and we're doing a greater than test. And so when we do greater than tests, we're only going to be focusing our attention in the upper or the greater than tail, the right-hand tail. So I'm kind of zooming in to that tail of the distribution. So let's start with a rejection region idea. So I'm going to draw the picture and say we're going to calculate a test statistic, probably get it on a printout. We won't have to do that by hand. But then we're going to evaluate it by taking whatever alpha we want to test at and putting it in the greater than tail. Now, the ideas I talk about in this video work for greater than tests, they work for less than tests, they work for two-tailed tests, and we're going to find this cutoff point here in the greater than test. We'll call it something crazy like Z alpha. So the ideas work regardless of which tail, large sample, small sample, it doesn't really matter, but I do want to compare the two. And so in the rejection region, what we're going to do is we're going to see where our test statistic falls. If it falls further out in the tail, that's called the rejection region. So you see things like at alpha equal 0.05, we reject H naught. If Z is greater than 1.645, if it's 0.025, that Z value is 1.96. And we've run into these numbers along the way. So this would be the reject conclusion out here. And then if the test statistic fell on the other side of that critical value, anywhere over here, this is the FTR, fail to reject, the null hypothesis. And so what you see in the notes here is rejection regions. We're going to compare the test statistic to Z alpha. Now the p-value approach is going to take a different approach, and the p-value is found, and we've talked about this. I'm going to get a different color ink for this. Let's get a darker color. Let's get a nice blue color here. The p-value is found by taking a look at the test statistic. So let me draw a test statistic over here in blue. Let's call this the test statistic. I'll call it TS. And we've seen the p-value is the probability of getting a value even further out in the tail. And so this blue shaded region here would be the p-value. And we've talked about how we interpret p-values. If the p-value is low compared to alpha, we reject H naught. And so that's what the second part you see here, compare the p-value to alpha. Now, what I want to think about is this p-value here that I've drawn in here. What happens if the test statistic's further out? And a lot of times I ask my live classes, I tell them, here comes a trick question. Ready? What happens to alpha as the test statistic moves further out? So assume the test statistic was larger. What happens to alpha? Nothing. Nothing happens to alpha. Alpha has nothing to do with the test statistic. What changes? Well, the p-value changes. In fact, if my test statistic was further out in the tail, I'm trying to do a real dark shaded region, the p-value gets much smaller in that particular case. And so the first test statistic I drew, let's call it test statistic 1 and test statistic 2 here. The first test statistic, p was low. The second test statistic, p is even lower. Both are going to lead us to reject H naught. What happens if I move the test statistic over someplace like here? Pretty close to the Z alpha. But wouldn't the p-value, wouldn't the shaded region beyond that test statistic still be low? In fact, what you should probably be realizing is as long as the test statistic falls in the rejection region, so as long as the test statistic, and I should line it up with the Z value here, as long as the test statistic falls over here, the corresponding area beyond it, the p-value is less than alpha. But if the test statistic falls over here with this beautifully straight line I just drew, sorry about that, let's call this test statistic 4 now. Well, now the p-value is large compared to alpha. And so what you should realize, as soon as the test statistic and the Z alpha value switch spots, one's bigger, then it switches and they change kind of locations, that's the exact same moment that the relationship between alpha and the p-value switch as well. Rejection region method, we're comparing numbers, test statistics to Z alphas on the number line. P-value method, we're changing the comparing the corresponding areas in the tail. And so really what I want you to think about is how these two values, the test statistic and the p-value, are a team. If you give me a test statistic, I can tell you the p-value, or better yet, the computer can tell me the p-value. These two are also a team. Usually you specify alpha and we come up with a critical value. And so when it comes to making a conclusion, if you do a rejection region, you take the test statistic off the printout, you go to the table and find a z alpha to make your conclusion. If you use the p-value approach, the computer gives us these two, the computer gives us the p-value, all we have to do is compare it to alpha. It's generally considered an easier way to make conclusions. All right, now let's turn our attention to working with proportions. And this is the same notes we've had before, right? There's 4 steps to the test of hypothesis. The first one specifies a null and an alternative. Here, the null hypothesis, the alternative are going to be p is equal to some hypothesized value of p. The alternative is going to be p is not equal to, or greater than, or less than, or one of the 3 alternatives. The test statistic is a number on a printout. And I should mention, some textbooks, some people use p bar to represent the sample proportion. Some use p hat. It's neither here nor there. They're just symbols. It's a sample proportion minus hypothesized value divided by a standard error. It's a number on a printout. You don't ever have to calculate the test statistics for us. When we're working with proportions, we need to be working with a large sample. And for proportions, a large sample is n times p and n times q. Both need to be greater than or equal to, and this number changes from person to person, from textbook to textbook. I'm going to go with 15. N times p and n times q both have to be greater than or equal to 15. When you're doing a test hypothesis, we assume the null hypothesis is true until we reach a contradiction, and so we use n times p naught and n times q naught. And q naught, sometimes we call it q naught, other times we use just 1 minus p naught. Q is kind of the opposite of p. Q and P have to sum to 1. Q naught and P naught have to sum to 1. So we identify the test, we get the test statistic, we do one of our 2 different methods of making conclusions, evaluating a test statistic. We have rejection regions, we have p-values, and we make conclusions. And as we've seen before, it's the same stuff. I'm just copying and pasting these notes because the one idea I really want you to understand, there's one test hypothesis technique. There's lots of applications. We've seen a large sample for a mean. We've seen a small sample for a mean. Now we have a large sample for a proportion. I should mention, there is not a small sample test for a proportion. Remember when we were working with means and we had small samples? We had an extra assumption. We needed the population that we're sampling from to be approximately normal. Now that we're working with proportions, it's because we're working with a categorical data or a variable. So I'm asking questions like, do you have a tattoo? Yes or no? Are you a senior? Yes or no? We're looking at more like a binomial, right? Successes and failures. Yes, you have that characteristic, or no, you do not. There is absolutely no way when you're working with a categorical variable that you're going to get a normal population. That's the assumption that's needed for t-distributions to work. And so t-distributions can sometimes work for means. They'll never work for proportions. And so we'll have a large sample test for a proportion, and that's it. No small sample work. So let's get in and take a look at an example. We'll look at working from both the rejection region approach and also the p-value approach. So streaming of television programs is trending upwards, has been for many years. A recent study claims that 2/3 of all Americans qualify as subscription streamers. A recent study of 2,242 elderly adults, wow, that looks like a big sample. Be careful with that. Found that 1,560 would be considered subscription streamers. On the basis of this sample, can we conclude that the true fraction of elderly adult subscription streamers differs from 2/3? So we want to test to see if a proportion differs from 2/3. How do we set up the null and the alternative? Well, the thing that we want to say is what we list as the alternative hypothesis. We want to say a proportion differs from 2/3. We put an equal sign in the null. If I wanted to show that the proportion exceeds 2/3, I do a greater than test. If I wanted to show the proportion is less than 2/3, we do a less than test. But this asks for a not equal to test. That's why we do the not equal to in the alternative. Now, in order to find a test statistic, I need a printout. And so I put the data into a printout or into an Excel spreadsheet, and I had a template that I've created. And here you go. The template asks me to enter in the number of the sample size, or the size of the sample, the number sampled, and then the number of successes, the number of yeses. It gives me, the template gives me that. I had to put in the 2/3 value here as a hypothesized value, and all the values down here are calculated by this template. And so in this particular case, whoops, that's fun. There we go. I'm trying to get to the test statistic here of 2.9336. Now, is this a large sample? To determine if this is a large sample, we have to take n times p naught, which is going to be 2242 times 2/3, and we have to take n times q naught, which is 2242 times 1/3, and see what those products are. And so we need a calculator to do a little bit of math. I don't have a calculator handy, but I do have my cell phone, and that'll do the trick. Let me get to my calculator here. I should probably have this queued up. Sorry about that. But I'm going to take 2242 and multiply it by 1/3, and I'm going to get 747. Where is my cursor at? There we go. Equals 747.3. Well, that's bigger than 15, and then you multiply it by 2/3. It's obviously going to be a lot bigger. 1494.666. So I'll make that 7. Because both these things are at least 15 and is large. Notice I didn't use 30 or more anywhere here. This is the sample size criteria we need for proportions. Now I can move forward. I can go ahead and evaluate the test statistic. And the first way I'm going to do it is to use our rejection region technique. Remember, we have two techniques. The rejection region says, all right, let's work with a normal curve. But when we work with the normal curve and we're working with a two-tailed test, I got to put half my alpha in the upper tail, half my alpha in the lower tail. So I'm going to put 0.05 over here. I'm going to put 0.05 in this tail as well. We're going to find those cutoff points. We've done this many times before. You can either use the norm inverse function, or you can use a cumulative normal table, but you're going to get a rejection region of z less than negative 1.645 or z greater than 1.645. And now we compare our test statistic. We take a look at the 2.9336, and it falls way out here in the upper tail, and so our conclusion is we're going to reject. There's sufficient evidence to indicate that. And now I'm going to say the true fraction of elderly adult subscription streamers. That's tough for me to say, apparently. I'm going to take this wording in the problem here, and I'm just going to copy and paste it. The true fraction of adult subscription streamers differs from 2/3. If my test statistic did not fall in the rejection region, we'd fail to reject. There's insufficient evidence, but the rest of the word stays the same. What's the assumption we need in this case? We just need a random sample. And in this case, we were working with elderly adults. So we got our test. That's the null and the alternative. The test statistic comes right off the printout. The rejection region, the conclusion. If we decide to use the p-value approach, well, most things stay the same, right? The test, h naught, p is equal to 2/3 versus the alternative, p is not equal to 2/3. The test statistic is still 2.9366. That doesn't change, right? We get that same number. But now we come down here and find our p-value that matches the test. So the p-value that we're going to use is the 0.0034. And now all we have to do is compare that 0.0034 to our alpha. Is it low? You bet it is. In fact, the rest of the stuff stays the same. At alpha equal 0.10, we reject h naught. There's sufficient evidence to indicate the true fraction of elderly adult subscription streamers, said it better that time, differs from 2/3. What's the assumption? Same one. We need a random sample of elderly adults. The rejection region technique or method of making conclusions, the p-value technique or method of making conclusions. They both will give you the same answer every single time. Now, if you use alpha 0.05 for one of the techniques and alpha 0.01 for another, that may change. But if you use the same alpha for both techniques, it's always going to give you the same conclusion. I'm a big fan of the p-value technique because a lot of the work's done for you. Rejection regions aren't all that difficult. Given the path we've been on this semester, we've seen normal distributions, we've seen t-distributions for a while. But what happens when we move to some tests and some confidence intervals later on that you work with chi-squares and f's? Well, I'm going to tell you now, working with other distributions, it's not that much more challenging than working with the z or the t. But the bigger point is, why do you need to? If we allow the software to generate confidence interval endpoints for us, if we allow the software to calculate test statistics and p-values for us, that makes these techniques, these inferential techniques, the confidence intervals, the test hypothesis, a lot easier, a lot more manageable. We get the same information, and we allow the software to do a lot of the heavy lifting for us. It's a win-win. So that's what I'm going to encourage you to do. Now again, for my class, you're taking an Intro to Business and Economic Statistics 1 class here. You're going to have to do some rejection regions. You're never going to have to calculate confidence interval endpoints, but I will ask you to do a rejection region a couple times this semester. But far, far more often, you're going to be interpreting p-values. So make sure you know how to work with both techniques. And that is just another example of a test hypothesis. Our sample size criteria changed. The assumption, we need a random sample. But other than that, it's pretty straightforward. So when you have questions, you know how to get hold of us. Good luck.